I can skip this slide. So this is one of those things where the presenter goes and puts another hat and changes clothes and comes back and presents. So this is one of those things. But I understand that. So we'll go. So this paper is different, very different. It's about software components. It's more about software architecture. So if you're interested in software architecture, especially embedded architecture, that would be more of an interest for you. And it's talking more about design and runtime, the difference between the two. It's the same authors. Where is it now? So that's, I think it's good, but not a problem for some reason. I can just, oh, what happened? Maybe some, maybe your screen.
So sharing is okay?
Yes, okay, let me just see if I can.
What's...
Yeah, this is it.
Now it's okay. Yeah. It's perfect.
Yeah. Okay. Yeah, okay. Sorry about that. Okay, so the main point, first I'll talk about the motivation. The idea here is to come up with a universal standardization of software component interfacing. Just the interfaces and what components do. And the motivation is the first thing I'm going to talk about. Then I'm going to talk about the definition of software component. And then I'll spend some time on dynamic reconfiguration, which is very important. And you heard maybe a little bit in the previous talk where we have to have systems that are deployed today, but then they have to update themselves and adapt themselves and change themselves as they go. Then I'll talk about the component compliance and equivalence and the actual interface implementation. And finally, I'll talk about the automatic parsing of the specification and an example that I have worked on based on a real language that describes an interface. Okay, so the reasons for this work are many. And as you can see, one of the main reasons is really the reuse of components that come from third parties, come from people that really develop their components in place, but they have different teams and they have to coordinate. People who are maintainers, who want to maintain large systems, and also systems that have to adapt in changing environments. And one of the motivators is also the third-party component examples, because we have all these cars. So if you make a car and you have all these different modules, hardware modules, then imagine how many software components have to go. You cannot develop all that by yourself. If you're a company like, let's say, Toyota or Honda or Audi or some other company, so they have to buy some components, hardware, software, and put everything together. And that's becoming a challenge. And I believe that some of it comes from the interface specification. Okay, so now let's talk a little bit about what is a software component in general, because it seems like there are many definitions, and I just want to say the first bullet that it's just something that involves some functional and non-functional software requirements. And all of this is really describing the definition, can live in a separate context, and it can also have subcomponents in itself, but it presents a unique and defining interface to the world. And that's the important thing, because this is how we use the component, right? How can I use a component if I don't know what it can do? It can also have an internal state and some self-diagnostics. So this is kind of a fuller picture of what when people say component, they just talk about the interface, and they don't really say what the interface is sometimes. So I just wanted to add all these other characteristics because they're really important to understanding, and so that they can give us the opportunity to do all these dynamic changes that we want to do. So, what is dynamic reconfiguration? I'm going to talk about that in the next two slides. And the main thing about dynamic reconfiguration is that 99% of the systems are probably static. They're just deployed, and we have certain components that work between themselves. They do certain things. But if you wanted to just go and change a particular component on the fly without perturbing the entire system, very few systems have the mechanism to do this with any component that they have. And that's something that could be changed, but it requires certain discipline, certain requirements for the way we design components. So now every component has a state. Imagine that you have a component A and you have a newer version that is component B that has changed, but you have some state that this component is in at the moment, and by replacing it, you would like to inherit that state so that it can just pick up from where the other one left off and the entire system can continue. Similarly, each component may have a configuration parameter that it reads on startup and comes up with those parameters and knows what to do. Another thing that's important is not all components have that, but it's important to have a diagnostics interface so that you can control and basically know what the component is doing at the moment, whether it's servicing the transaction, whether it's initializing, where it's ready to run but doesn't do anything, it's idle. So all these things that I've talked about so far could be worked out in, very easily in a publish-subscribe architecture that I described in the previous presentation. For the PX4, for example, or ROS or ROS2, which is a robotic operating system, is very popular. So the publish-subscribe is really good because it has this loosely coupling model that people in computer science like to talk about, and it's really paying off to build systems that are extendable. They don't make all these weird dependencies. When you move one component, you can put another one without disturbing the rest of the system. Okay, so this is the dynamic reconfiguration of the file. So imagine that you have a component repository where the components are stored, and then you have a component manager. And you work with component A and component B in a first configuration. Then all of a sudden, let's say you're a robot that goes to a normal situation like this, but then all of a sudden goes into a dark forest and the environment changes, there is not much visibility. It all of a sudden needs to change these two components to other components so that it can adapt better. It could be more efficient. Maybe it can save more battery life. All these different reasons that you can think of. That can happen only if I can replace these components in a way so that the system can continue to work without any perturbation. Now, this can happen only if I have compatible interfaces between components. So if I wanted to replace A with C and B with D, then I have to make sure that A and C have the same interface, or at least an interface that's compatible. And then this could be done at certain moments only. So the system, imagine the system is doing something. If a component is in the middle of some processing, you cannot really do that. You can do it only when the component is servicing something and it's done at the moment. It could be just for 10 milliseconds that it's busy, but you have to wait for it to finish and then do something. Similarly, we have to look into the real-time aspects of this. Can we do this with real-time systems? I mean, yeah, you could, because if it takes like 1 millisecond to replace a component, maybe you could in certain situations. If it's like maybe very hard real-time, maybe not. So it's still a call, depending on the system, but it seems like we have to take into consideration the real-time aspects of these systems. And then the other thing is we're replacing portions of the code with other portions of the code. There's always security issues. If somebody has put some different code maliciously, how do we make sure that we can authenticate and say, oh, this component is mine. It's legitimately created by somebody, and I know that it belongs to my system. And then I can instantiate it and let it go. So these are the things that we have to think about. How things can work with dynamic reconfiguration. So this is not very new, but at the same time, it's not like there is a universal way to do dynamic reconfiguration. There are papers that propose different ways to do it. But one of the issues is, I think, the interface problem with the components. So here's this is like the main slide here in the presentation. Here's a depiction of a software component where we have the functional part here. And this is pretty much all these things are the main portions of the interface that are related to the functionality of the component. And I have introduced this block and this block also. So we'll just go over this one by one. But this part is modeled after the robotic operating system. And so we have the incoming messages, which is messages that the component receives from other components. We have outgoing messages that are the messages that the component responds to. And then we have services. These are all sets, by the way. So it's like sets of services, sets of, and these are actions. So all these are functional. And then we have configuration parameters. And then we have the state of the component, internal state, which is like a bunch of variables that the component keeps some data in that is dependent on the operation of the component. Then we have a separate interface here, which is like a delta interface, which receives messages from somewhere, and it can just check the sanity of the component and whether it's doing something at the moment or not, and it can control it, whether it can take it down, put it offline, unload it, load it, things like that. So this is like a maintenance and diagnostics and control interface this here. So this is really the contribution is really creating this picture with all the things in one place and what are the things we have to worry about and how we can describe an interface, including this. Because not all components have, for example, parameters, configuration parameters. Not all of them have state. Maybe some are stateless, right? I mean, that's very nice if they're stateless because one thinks less to worry about. But in the general case, we can have configuration parameters, we can have states, we can have all these different messages, services, and actions, and we could also have diagnostics. So this is really the most general way to describe it that I have come up with. And there are examples, if you look into the ROS implementation, robotic operating system, and into autopilots like PX4, autopilots, and other similar implementations, you could see that they have components that have all these things. Now, what is the main problem and why I decided to write this paper was because all these interfaces are all over the place. Sometimes you have a small text file that describes maybe this, another text file that describes this, another text file that describes this, set another one for this, maybe another one for this, nothing for this, and nothing for this. But all of this is in all separate places. In main situations, this is in code, this is in code, part of it is in text files, and part of it is in code, so everything is completely inconsistent. So if I take a component, I have to know this architecture very well, and to look for this information in order to be able to present it to somebody. So if I take a system, or a component from certain system, and system A, let's say, and have to port it to another system, I cannot say how this interface translates directly. I have to basically do a complete rewrite almost. So that's why what I'm saying, if we can take all this stuff and put it in an external way, in some structured way, so that we can have a way to parse it and look at it, and make sure that the component can be, so the interface is basically not related to the implementation, so we don't have this mix of code and interface. And I think that idea is not new as far as dividing interface from code, but this is like directly looking at the implementation and the way to do it for a particular class of systems that I have looked at. I mean, there could be other ones, but this is mostly, since I'm mostly doing robotics and embedded systems, And this is where I see the different take on different developers. And you know how people have, the main goal is to make it work in robotics. And that has been the goal in the last 20 years. Make it work, make it work. Don't worry about security. Don't worry about reusability. Don't worry about maintenance. Not that people say those things, but that's what ends up happening. So here I'm coming up with some definitions of how to make a component be compliant. So this is like if I have a component with interface I1 and I2, then if I have a component that is a subset, the interface is a subset of the other interface I2, we can say that all these other subsets here that we have the messages, the outgoing messages, like here, they all have to be like that. And given that, the difference, what is added to the I2 is not used. Then we can say I could use this component. But if something is used from this component, which is like a superset, then I cannot really say that this component is compliant. So this is just a formal way to describe what it means. And then in the next slide, this is the ideal implementation where we say they have to be completely identical in all these parts. So in order for us to say that the interface 1 is equal to interface 2, we have to make sure that all these parts are the same as far as their sets. Otherwise, we cannot guarantee that. Now, how can we implement it? How can we describe an interface? So one easy way is to just go and use something that already exists, like JSON or XML, and say, oh, I can describe all things in a structured format, and then just use a standard JSON parser and make sure that I have a component that complies. A better way, I think, is to create a domain-specific language, which is right here, which is specifically targeting the description of components. Now, when we have a domain-specific language, we have the definition of formal grammar. Like in the BNF format, we have a formal grammar, and it's much better. Then we can do automatic parsing, we can do code generation, then we can use these tools. Now I have a very similar second slide. So the preference is to use your own language using existing grammar, because if you have a grammar, it's better to not have, it's much better than have like a free-form language of some sort, especially when we want to describe something that really has data and types. If you look at what component interface it will have, if you have a message, it will have maybe input parameters, and it will have outgoing message will have all these other parameters. So similarly for services, you'll have input parameters and output parameters for services. So one way to approach that is to use something like interface definition language, like Thrift. This comes from, I think, from Mozilla, if I'm not mistaken. But Thrift is a kind of popular way to express interfaces between different entities. It's mostly used for things like web services and stuff. But this is an example that has the grammar published. So you could just go and download the grammar. And if you use something like Xtext or Antler, you could just add new things to the grammar to basically do what you want to do in the interface, because it's not going to be sufficient what they have. Or you could design your own grammar based on some example like Thrift. That's another approach. But the important thing is to have this grammar. Okay, so here's an example of the additions that were done so that we can describe an interface. So if you look, if we have just one message one, we just describe the type of the actual field and then the name of the field. If we have a service, then we describe similarly the fields. If we have an action, and so forth. For the configuration parameters, similarly. For the state variables also, and then for the diagnostics also. So you could have the entire interface in one place, not parts of it in code, parts of it in one file, second file, third file, fourth file, and so forth. And then when the component starts, it would parse this, make sure that it conforms to the grammar, and then instantiate everything. Then what happens is later on, let's say 6 months later, somebody came with a modified component and gave us that same interface and said, this is the interface I present. Then we have some assurance that going through the tools we have, and this could be much bigger, this could be several pages, right? So if we run it through a tool, the tool will tell us this component is exactly compatible, or it's not, and then we can talk about dynamic configuration. So this is the actual grammar. If you're familiar with the BNF kind of type of grammars for Antler or for Xtext, these are the things that need to be added in the grammar in Thrift so that we can support these new things like messages, actions, configurations, and state. And here you can see up there, service action, configuration, message, and state were added to the definition clause, which means that we're now supporting it. And it's that easy to add more things to the grammar. Then what happens is you have to obviously go and work on the actual parser once the parser is generated from the grammar to add actions to what you do when you encounter an identifier like that. But this is just something. So for example, the code generation that we can talk about here is we can have an interface file, we can have a specialized parser that we generated from the grammar, right? And then we can then parse these components, and let's say it has this particular interface. Then I could go and generate all the boilerplate code for Rust, for example, in the top, and then for pxplore in the bottom, and depending on what I want. And then I'm using the same parser, and then I have maybe another, after the parser, I have this other block, like architecture one, specific code generation. So if I added a third architecture, I'll add a third block here, and that block will allow me to generate architecture-specific code. That way, what happens is there are two things. One is, first, I'm skipping the opportunity for error, and second, I'm improving productivity, and third, we're using a parser that makes sure that our interface complies to what we want to comply. So that's just the idea of how interface handling for components could be solved. I'm actually implementing that with Thrift, since I'm more of a C++ person, and I kind of refuse to use some other language when I can, but it could be done in Java or Python or anything like that. You could take that grammar and run and basically write your own parser in whatever language you like, and then you will have a similar result. And that's what I did with the Thrift grammar, which seemed to be simpler to manipulate compared to other ones. So what do we gain by going in that direction? So these are the advantages of the interface standardization that I'm just talking about. We have one way to document components, because if you have an interface in one place, this is a pretty good start for documenting what the component does. Then we can use all these programmatic tools that pretty much eliminate or minimize human error. And then we can generate code, some of the code that we don't want to write, and could be written that way. And we can also do the dynamic reconfiguration where we could take one component and maybe send the interface to a vendor. They could develop a different component, send it to us, and then we can just use it as an upgrade to the existing component. And this way, we can really accomplish what people are saying all these years. We can do component implementation separate from the interface. So because if you remember when Java was introduced, that was the main thing, right? And Ada too. Ada has interface versus implementation separation. So this is not new as far as, but this is for programming language. So I'm just talking about software components as structures that we develop as software engineers. And I believe that's what I have.
Thank you very much.
Thank you.
Question, please.
Yes.
Yes.
So how safe is this dynamic change of configuration?
The dynamic reconfiguration. Yeah, so safe in what respect?
If you can fail and nothing will be working anymore.
Right, so, yeah, so sometimes, maybe sometimes it actually can help in the opposite way. If you have a failed component and you want to replace it with a good one, so it could actually help the system. But at the same time, what you could do is you could stop the working component, load the new one. Once the new one has caught up with state and everything, then you can switch them. You have to develop a protocol for that. Now, this is a good point. I mean, these are the fine points when you go into the implementation mode. Now, this is a good question. Thank you.
Yes.
Yes. Yes. There could be, yeah, there's some challenges, but it's like everything else. You have to invest into what you believe in order to get something back. There's some, I don't see too many, I find this to be an approach that requires more discipline than the current approaches that have basically no standardization. And I don't see why there should be no, because I mean, I originally finished a double E degree here in the University of Sofia. And if you look at the hardware component and you read the data spec, that's precisely what you get. It tells you the temperature range, it tells you the number of pins, it tells you the voltage range. And if you violate those, it doesn't work. Now with the software components, we have all the freedom in the world. We do whatever we want because we can, right? We're software engineers. So what I'm trying, is there a way for us to make things a little bit more organized in a way so that we can improve reuse and we can just improve component maintenance and future development? Because if we have systems that will evolve, that will become more complex, it will become even more challenging to control the quality of our software. So this is really, you have to kind of pay a little bit more in development. So the challenge is that it will be more expensive, most likely. It may take a little bit more time, and it will take some runtime also, impact, right, from the runtime, because you have to replace a component. If you replace more than one, you have to wait in particular. So it's not a universal solution in all situations, but it's more of a method to resolve certain issues at runtime. Yeah, so I'm not sure if I answered your question.
Standardization when you have a lot of organization that also involves discipline, and even to come up with certain standards, you don't really something that's really great, but comply with it, right?
Yeah, but if you look even the auto manufacturers, they have this AutoZar architecture, which has some component standardization, but it's not so formal as this. They have something, and they have a lot of big documents, but it's not precise. They don't have like a language or something. It's not formal. They have kind of recommendations, and that's good. But it's I know, because people, especially people that just come out of software schools, they're just told that they can write their software the way they want most of the time. And that's good because you're creative and you can do different things in very interesting ways sometimes. But I think for safety critical systems, for robots and things that really can kill people and do things like avionics and stuff, I think we have to have a better approach. That's my belief. And if you have to pay more for this approach, so be it, because I think it's worth it. I still didn't answer your question, right? No, it's okay. I mean, yeah.
Thank you very much. Just to see if there are some questions from the online audience, but we have lack of time now, so maybe just short question if there is. Still no, it seems. Okay, thank you very much again. you.